Hello folks, welcome back. This is Armin Pantalone, the Chief Technology Officer for Giga-tronics, welcoming you to another one of our TEmS Talks, TEmS being our Giga-tronics thread emulation system. So today what we want to accomplish is something, a very small subset and a small function, but a very important distinction between our thread emulator and some others out there in the market. And what we're going to highlight today is our ability with one piece of hardware to not only have a thread emulation system that's based on pulse descriptor words, but also the ability with the same piece of hardware, again, to add a complex modulation onto that emitter profile, which can't itself be described simply by pulse descriptor words. There are limitations to pulse descriptor words, and some other folks' hardware, you need a whole separate piece of hardware, sometimes very expensive, sometimes picks up a lot of rack space, to be able to do complex waveform creation that attaches itself to the same emitter as a normal pulse descriptor word. So we're going to try to do this quickly, and I just want to show you a very simple but complex waveform file that we're going to attach to emitter that's going to be played on top of just a pulse CW that a normal pulse descriptor word will create. Now we do have normal modulations, the linear frequency modulation, phase shift keying, frequency shift keying, etc. But those PDWs can't always describe a very complex waveform that you want to create. So we're going to show you a simple complex waveform that we're going to create just to show you the functionality and how easily you can attach a complex waveform file to play out of a certain emitter at certain pulses during your scenario. So to get started, what we have here is a very simple scenario. We have one system under test receiver in the battle space, along with one emitter spaced 5 kilometers apart. And it has 2 emitters on the platform 1, which is 5 kilometers away from the system under test receiver. And it has one emitter that's simply putting out a pulsed CW at our IF center frequency. This is our IF center frequency pulse at 1200 megahertz, and this is our RF output after it's up converted in the RF up converter to a center frequency of 10 gigahertz. So as you can see, this one particular emitter on channel 1 right now is just a very simple pulse CW with a fixed PRI and a fixed pulse width to create a sin X over X sync curve in the frequency domain. So the RF created that we just showed you was this particular radar mode, which is one of the many radar modes and engagements attached to that platform that was creating that. If we open that up for you to look at, this pulse group is very simple. It has a fixed pulse width, fixed PRI, and there's no modulation on the emitter. What we're going to do now is select a different emitter for the digital oscilloscope and also the spectrum analyzer to show that we can attach a complex arbitrary waveform generation file to be read into that emitter's pulse profile, and we're going to play that out. And what that one looks like, it's the exact same pulse, the exact same PRI, but this one happens to have a binary data file for the arbitrary waveform generation function to be read into to do a complex vector multiply along with the pulse CW to be played out on that emitter. And I'm going to show you in another second what that complex waveform file looks like. Okay. So in the previous scene, what you saw was we had an AWG file attached to that emitter. And what that awg.dat file is just a binary data file of I and Q values, in phase and quadrature. Both values are in columns, I and the Q, and they're both plus and minus values up to 32,767. Full scale counts on the D to A that's used in the emitter profile right now to feed into the DAC. And what that looks like when you plot it on Excel, we pull the data file into Excel and just we're plotting it. This is the I and the Q, the classic I and Q file for a 2 megahertz linear frequency modulation. And then after 1024 chips of that IQ LFM is played out, we're doing nothing more than holding Q constant, and I is going to ramp down from full scale to 0. So what you should see on the pulse CW is first a modulation of 2 megahertz, and then you should see an amplitude taper for the second half of the pulse down to 0. Okay, to switch from the pulse CW to the arbitrary waveform generation file and the complex multiply there of both the chirp followed by the amplitude taper, we're just going to stop the scenario. We're going to go back to editor mode, and we're going to do nothing more than swap the priority of the two emitters in the scenario such that it switches from the one that's pulse CW to the one that has the arbitrary waveform generation file attached to it to enhance the PDW playout for that complex waveform we showed you. So we'll save the file, go back to the simulation mode, and play that out. And what you see now is a totally different waveform pulse parameter, with the first half being the chirp and the second half being the amplitude taper. And what that looks like on your spectrum analyzer is a 2 megahertz chirp, and then when you see the amplitude taper, that's the pulse CW sticking out through the center of it. So what we showed you in our shorter vignette today is just a very important specific function of the Giga-tronics thread emulation system, and that's the ability, while it is a PDW, a pulse descriptor driven interface that runs the simulation and all the emitters in the background noise, the background noise and some other important features, or some very complex emitters, can be synthesized with our hardware by using a complex waveform file, an AWG file, arbitrary waveform generation file, attached to certain pulses and certain emitters. So we showed you just how easy that is to do, what the import looks like. It's a very simple format for the data file to pull it in. And the important thing here too is the hardware that we use is one single piece of hardware. To be able to do complex waveform on top of PDW-driven RF, you do not need any new hardware. You don't need a second box. You don't need to add to the rack and stack of your equipment in the bay. Use the same piece of hardware and just bring in your own synthesized complex waveform files, and then you're off and running. So as usual, thanks for coming to our TEmS Talk today. And again, as a piece of advice and caution, we are what we call professionals, so please don't try this at home.